Now we're going to talk about inferences that we can make from comparing results from two different samples. In the first video, we'll talk about inferences we can make about two different proportions. The two methods we're going to use again are the p-value method and the critical method. A lot of steps are going to seem really similar to the previous videos on hypothesis testing, so make sure you're pretty well versed in those videos before you start these. Okay, p-value method. So here are some tools that we need for testing a claim involving two different proportions. The z-value, the test statistic that we're going to use, since this is proportions, is given by p1 hat minus p2 hat minus p1 minus p2, where p1 hat and p2 hat are our sample proportions from the first sample and the second sample, and p1 and p2 are our population proportions, divided by p bar and q bar, which I'll get to in just a second. N1 and N2 is the number of items in the first sample and the number of items in the second sample. Okay, p bar is called the pooled proportion. It's the sum of the variables divided by how many in the samples total. Q bar is its complement, 1 minus p bar. All right, this will simplify things a little bit. For our purposes, the null hypothesis will always be p1 equals p2, which means that p1 minus p2 will always be 0. So our test statistic simplifies to just be p1 hat minus p2 hat over that square root of p bar q bar over n1 plus p bar q bar over n2. So write that test statistic down. That's what we'll be using for every problem. Okay, let's practice. So first example. Given the data below, use a 0.05 significance level to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags than those without airbags. So we have 41 fatalities if the airbag was available, compared to 11,541 total occupants, and 52 fatalities if there was no airbag, compared to 9,853 occupants. So to get started, these first several steps are going to be just like they were in the last couple sections. First, we need to identify the claim. So for this, let's let P1 be the proportion of fatalities in cars with airbags, and P2 be the proportion of fatalities in cars without airbags. The claim is that the fatality rate of occupants is lower for those equipped with airbags than those without, so P1 would be smaller than P2. And the next thing you always have to do is identify the opposite. So the opposite of the claim is P1 is greater than or equal to P2. Now we need to tell which is our alternative hypothesis and which is our null hypothesis. So you notice here we wrote the null hypothesis is P1 is greater than or equal to P2. We actually mean P1 equals P2 so that we can use that test statistic from before, but it needs to have the equality in it somewhere. And the alternative hypothesis is apparently the claim, P1 is strictly less than P2. And then identify alpha, the significance level. In this case, alpha is 0.05. Okay, let's find this test statistic. So here's P1 hat and P2 hat, and then the pooled proportion. So P1 hat is 41 out of 11,541, so 0.0036. And P2 hat is the sample proportion for no airbags, 52 out of 9,853, 0.0053. Now our pooled proportion is 41 plus 52, so all of the fatalities divided by all of the total occupants, 11,541 plus 9,853. So we get 0.0043. So Q bar is the complement of that, 0.9957. So we take those values and plug them into our test statistic formula for Z. what we get is negative 1.91. Okay, so remember, this is our test statistic. If we're using the p-value method, the next thing we need to do is find the p-value. Okay, now remember, the p-value is, in this case, the area to the left of our test statistic, since we have a negative z. So using the normal distribution table or your calculator, we're going to find the p-value that goes with z equals negative 1.91, the area to the left. And that should be 0.0281. Now a quick comment here about the z-value before we move on, the p-value before we move on. If this had been a two-tailed test, we would need to double the p-value because the area would occur in both tails. Since this example is a left-tailed test, we don't need to do that. In our next example, we will worry about that. So for right now, 0.0281 is our p-value. Now, before we can interpret the results, we need to compare the p-value to the significance level. So since our p-value is smaller than the 0.05 significance level, that means that it's in the critical region. So it's a very small p-value, so it's smaller than the significance level. So it's in the critical region. That means that we reject the null hypothesis. Okay, now remember, our null hypothesis is always that P1 equals P2. The original claim was that P1 is less than P2. So if we're rejecting P1 equals P2, then it does appear we have enough evidence to support the claim that the fatality rate with airbags is lower for those in cars with airbags. The fatality rate with airbags is lower for those in cars equipped with airbags. Okay, let's do another example. In 1993, a survey of 560 college students said 171 said that they used illegal drugs during the previous year. In a recent study of 720 college students, 263 said that they had used illegal drugs during the previous year. Use a 0.05 significance level to test the claim that the proportion of college students using illegal drugs in 1993 was the same as it is now. Okay, again, really similar steps. The claim is that the proportions are the same. So P1 equals P2. The proportion of college students using drugs in 1993 is the same as it is now. The opposite then would be that they're not equal to each other. P1 does not equal P2. When we identify the null and alternative hypothesis, the null hypothesis must be the equality one, P1 equals P2. That means the alternative hypothesis is the other one, P1 is not equal to P2. Since there's no inequality sign here, this is a two-tailed test. That will be important for us when we calculate our p-value to double it. Okay, the significance level before we move to the test statistic is 0.05. All right, let's calculate that test statistic. So using our formula in black down there for the test statistic, P1 hat is the 171 over 560 from 1993. P2 hat is the 263 out of 720 from recent years. P bar is the total of the successes, so 171 plus 263 over the total sampled, so 560 plus 720, you get 0.03391. That means Q bar, its complement, is 0.6609. Plugging all that in along with N1 and N2 being 560 from 1993 and 720 from recently, we get a Z test statistic of negative 2.25. Okay, since we're using the p-value method, we need to find the p-value that corresponds to that Z test statistic. So let's do that. Since the test statistic is negative, we find the area to the left. Again, you're using your normal distribution chart, your graphing calculator, or maybe Excel. And we find the area to the left to be 0.000122. Now remember, this is a two-tailed test, so that is only the area to the left. We want both areas, so we double that. So the p-value is 0.0244. That is what we compare to our 0.05. So if we reject H naught, since our p-value is less than the significance level again, we reject the null hypothesis. If we reject the null hypothesis, that was the equality one, that was our claim. So it appears that we have enough evidence to reject the claim the proportion of college students using illegal drugs in 1993 was the same as it is now. Okay, let's do a couple of examples now using the critical value method. So, Chantix is a drug used as an aid to stop smoking. The number of subjects experiencing insomnia for each of 2 treatment groups in a clinical trial of the drug are given below. Use a significance level 0.01 to test the claim that P1 equals P2. So here's our group. So out of 129 people receiving Chantix treatment, 19 reported insomnia. And out of 805 people in a placebo group, 13 reported insomnia. Okay, so as we said in the statement, the claim is that P1 equals P2, that the proportions are the same. That means the opposite is that they're not equal to each other. And as usual, the null hypothesis is the equality one, P1 equals P2, and the alternative hypothesis is the two-tailed P1 does not equal P2. And in this case, the significance level is a little lower, 0.01. Okay, let's find the test statistic. So, using our formula for test statistic, 19 insomniacs out of 129 total receiving the treatment, compared to 13 insomniacs out of 805 total in the placebo group. The pooled proportion is 19 plus 13 over 129 plus 805, which is 0.0343, and Q bar is the opposite, or the complement of that, rather, 0.9657. And we're plugging all that in with our n values, and we get a very large z-value of 7.60. Okay, in this problem, we're using the critical value method, so we need to compare that to the critical value from our significance level. So we're going to divide the significance level equally between 2 tails. So we have a 0.01 significance level, which means each tail should have 0.005 in the right and the left. So we'd have 2 z values that correspond, critical values for z that correspond to that, either positive 2.575 or negative 2.575. Since we have a positive test statistic, we're going to compare our 7.6 to the positive critical value, the positive 2.575, and it is much greater than that critical value. So that means that it's in the critical region, so we're going to reject the null hypothesis. Okay, so remember, the null hypothesis was the claim that the proportions are equal to each other. If we reject it, then we don't have enough evidence to support the claim. We have enough evidence to reject the claim that the probability you will have trouble sleeping is the same with and without using Chantix. Okay, one more example. Inferences about 2 proportions. A Pew Research poll asked randomly selected subjects if they agreed with a statement that it is morally wrong for married people to have an affair. Among the 386 women surveyed, 347 agreed with the statement. Among the 359 men surveyed, 305 agreed with the statement. Use a 0.05 significance level to test the claim that the percent of women who agree is greater than the percent of men who agree. Does there appear to be a difference in the way women and men feel about this issue? Okay, the claim is that more women, a greater percentage of women agree with the statement or is greater than the percentage of men that do. So P1 is greater than P2, which means the opposite is P1 is less than or equal to P2. So our null and alternative hypotheses would be, first, the null hypothesis, we can say P1 is equal to P2. That would be the more reasonable one for this assumptions about our test statistic. And then the alternative hypothesis is definitely the P1 is greater than P2. Since this has a greater than symbol, it's a right-tailed test. Okay, and the significance level, it says, is 0.05. Okay, test statistic. So let's take the women for P1 hat. 347 out of 386 surveyed is 0.8990. And the men sampled, 305 out of 359 is 0.8496 sample, is a proportion for men. And our P-bar is the pooled proportion, so 347 plus 305 over everybody. 386 plus 359 gives 0.8752. So its complement, Q-bar, is 0.1248. Plugging all of that into our Z, we get a test statistic of 2.04. Okay, so let's figure out what this means. Let's use the critical value method here. Since it's a right-tailed test, we do not need to divide the significance level into two tails. We just need the positive critical value with a 0.05 area to the right. And that corresponds to the critical value for Z, 1.645. Comparing that to our test statistic is again greater than the Z value, so we reject the null hypothesis. It's in the critical region. So the null hypothesis was that the proportions were equal to each other. That's what we reject. So our claim being the alternative hypothesis that P1 is greater than P2, there does appear to be sufficient evidence to support the claim that the percentage of women who believe it is morally wrong to have an affair